this program, the vet tech program. Let's pick it up. All right, carbon dioxide. You've heard of this product. This compound. It is a byproduct of metabolism. I don't know if we specifically mentioned this or not, but I'll mention it now. The normal amount of oxygen that is consumed is 250 milliliters per minute. If we go back and look at our oxygen delivery, we have the oxygen content 20 times the cardiac output 5 times a factor of 10, so it's about 1,000. So we're delivering 1,000, we're only using 250. So we're only using about a quarter of what is available. The reason why that there is so much additional stuff there is because there may be times where we have a need for an increase in oxygen consumption, an oxygen demand, and you want to be able to supplement it. So if you have a situation where all of a sudden you need to do something stupid like run a marathon, you have additional oxygen available to you. Normal carbon dioxide production from metabolic activity, because it is a byproduct of normal metabolism, is about 200. We're going to call that ratio of how much oxygen is consumed to how much CO2 is produced the respiratory quotient, and it's basically about 0.8. And that's where that 0.8 in the alveolar air equation comes from, is the relationship between how much CO2 is produced to how much O2 is consumed. So good so far? Whatever you say, Rick. CO2 we know is it's primarily excreted by the lungs. We're not frogs. We're not small single cellular entities that can just release it through their membranes. We have to go through this complex mechanism of transporting it back from the tissues back to the lungs to be excreted. There are 6 ways in which carbon dioxide is transported. 3 of those 6 is within the plasma. 3 of those 6 are within the erythrocyte, and yes, we will know all 6. First of all, there is a chemical reaction that occurs when CO2 is present within the when CO2 is in the presence of water, and it's called the hydrolysis effect. CO2 and water form this intermediate substance called carbonic acid. Carbonic acid then dissociates into the bicarbonate ion and the hydrogen ion. We're going to call carbonic acid a very volatile acid, meaning it doesn't like to stay as H2CO3. It would rather go one way or the other. And it goes one way or the other, depending upon the location that we're talking about. At the cellular level, it's going to go from it's going to go from left to right. So our net effect is that we create bicarbonate ions and hydrogen ions. At the lung, it's going to go the opposite direction, because it wants to create the CO2 or move it back into the CO2 state and excrete it through ventilation. Normally, this is a very slow process. However, we're going to find that within the erythrocyte, there's an enzyme called carbonic anhydrase that speeds this up tremendously. Okay. Carbonic anhydrase. Enzyme that promotes the conversion of CO2 and water into bicarbonate ions and hydrogen ions. There's actually a couple other places in the body, one of which is the eye and one of which is the kidney, where the substance is located. Other than that, it's a real slow process. So let's talk about the plasma. In the plasma, CO2 is carried attached to some proteins as a carbamino compound as bicarbonate. So it goes through that process of converting itself from CO2 in water to carbonic acid to bicarbonate ions. So it's carried as bicarbonate. And it's dissolved. And this is what we measure when we measure our PaCO2. It's how much is dissolved in the plasma. It's the partial pressure. If I were to convert, and let me go back here and just make mention. This is measured in milliequivalents per liter. Does anybody remember what the normal value is? Okay, Rick, I'll give it to you. 22 to 26 milliequivalents per liter. That's the normal value for plasma bicarbonate. So as it's ionized, it's converted into that. What are these? What units of measurement are these measured in? Millimeters of mercury. Okay. For the arterial, it's 35 to 45. And if I'm looking at this, I'm looking at two different units. Okay. The relationship between carbonic acid and how much is dissolved, they're in equilibrium. So as the PCO2 level rises, the carbonic acid level rises. When one happens, the other happens. Okay? So there's a direct relationship. If I want to figure out how much PCO2 is present, but I want to express it in this unit of measurement, I multiply the PaCO2 by 0.03. So for instance, if I had a PaCO2 of 40 millimeters of mercury, I multiply that by 0.03, and I can say that I have 1.2 milliequivalents per liter of carbonic acid. I'm just basically expressing this partial pressure in the same units of measure that I would the bicarbonate. PaCO2 times 0.03. And we'll find it's an important component there. So we have three ways: dissolved, attached as a protein, and as plasma bicarbonate. That's how CO2 is carried inside the plasma. Inside the erythrocyte, it's exactly the same thing. Dissolved, and if you'll notice, the dissolved was 5% in the plasma. It's going to equilibrate with what's inside the erythrocyte's fluid. Same 5%. Are we missing slides here? Okay. So 5% of it's dissolved in the plasma, 5% of it's dissolved in the intracellular fluid of the erythrocyte. 21% is bound to a protein, where a very negligible amount was bound as protein, carbamino compounds in the plasma. Here it's pretty significant. And that protein specifically is hemoglobin. So hemoglobin on the way to the tissues is carrying oxygen. It gets to the tissues. The Bohr effect kicks in. There's a higher CO2 level at the tissues, so the O2 unloads. There's a rightward shift. Oh, God. He's talking funky words. Don't cry. That's safe for Wednesday or Thursday. That release of oxygen now frees up the hemoglobin to carry carbon dioxide. It's a pretty cool thing. One gets on, one gets off. Some have expressed it as, you know, when you go to Cedar Point, you got the roller coaster. One set of people get off the roller coaster, another set of people get on. It's just an exchange. And that's what happens in this case. Hemoglobin now becomes the carrier for carbon dioxide. The vast, vast, vast majority, however, is carried as bicarbonate, or is converted to bicarbonate, because of the presence of that enzyme carbonic anhydrase. Dissolved, carried with a protein, converted to bicarbonate. Oh my God. I believe you have this blown up in the back for you. Here's my tissue, my little mitochondria, producing metabolizing oxygen, producing CO2, right? That CO2 then is carried in a couple different fashions, we said. 10% of it is dissolved into the plasma or attached to a protein as a carbamino compound, or converted to bicarbonate and hydrogen ions. Very slow reaction because there's no carbonic anhydrase. The other 90%, the bulk of it, is either dissolved into the plasma as PCO2, same as we had out here. It's attached to a protein, in this case specifically hemoglobin. And it goes under the reaction because of the presence of carbonic anhydrase in a very rapid fashion, creating bicarbonate ions and hydrogen ions. Cake, right? They covered this in the E&P. That was a joke.
The 10% on top of that exit out of the body, or
it all eventually gets that's probably a bad way of putting it. The goal is to get this from the tissues back to the lungs. Okay? And I think there's another slide which shows this at the alveolus in reverse. Yeah. But let me talk a little bit about this whole hydrolysis event, because that's a very, very important process that goes on. I'd say, am I okay? But I know that I'm not, so why bother even? Did I mention this is on a test? I'm kidding.
I was really starting to cry.
We buy the Kleenex.
It's a good spot.
All right. CO2 in water forms carbonic acid. That dissociates into bicarb ions and hydrogen ions. And you'll notice there's arrows going both ways. This will fly whichever way it needs to. That's why it's called a volatile acid, because it has that ability to be able to go in and out of status. And there's snow in Carroll, just in case you're wondering. Those free hydrogen ions, those hydrogen ions that are present are available for reactions, and specifically this is what causes a substance to become acidic, is the presence of excess hydrogen ions. Something that absorbs that hydrogen ion we're going to consider to be basic, or a base. The process of taking care of excess hydrogen ions is called buffering. If you've ever watched the commercial for Tums absorbs 20 times its weight in excess stomach acids. Blah, 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 blah. Right? It's absorbing it. It's absorbing it by neutralizing that free hydrogen ion. In your stomach, you have an exceedingly acidic substance called hydrochloric acid. It's nasty. Those free hydrogen ions, if left unchecked, will cause damage. So what the body does is it buffers it. It neutralizes it. It ties up that hydrogen ion so it can't get into trouble. Because by itself, that hydrogen ion is not a pleasant person to be around. The primary buffering mechanism within the erythrocyte, because that's where this equation goes hog wild because of carbonic anhydrase, that free hydrogen ion is buffered by hemoglobin. So not only does hemoglobin carry oxygen to the tissues, carries CO2 back to the lungs, it also buffers hydrogen ions. So that intracellular fluid within the erythrocyte does not become extremely acidic. If it did, cell wouldn't live. In all truth, what kills you eventually is free hydrogen ions that aren't checked. They make the mitochondria not function well. They basically just wreck the whole machine. These evil little things. So we need to buffer them. That's what the hemoglobin does. So hemoglobin ties up to hydrogen ions. The bicarbonate ion goes through a process where it diffuses back out of the erythrocyte back into the plasma. It then joins up with some sodium and is carried as sodium bicarbonate back to the lungs. We call this the chloride shift. So bicarb is produced through the process of hydrolysis in the erythrocyte. It moves out of the erythrocyte back into the plasma. Well, hold on, Charlie. I got a negative ion moving from point A to point B. I could now have an electrical imbalance there. Well, what ends up happening is chloride moves back in. There's an exchange for bicarbonate for chloride within the erythrocyte. Down on the bottom here. Bicarb moves out of the erythrocyte back into the plasma. Chloride moves out of the plasma into the erythrocyte. It's called the chloride shift. Where sodium was attached with chloride previously, sodium says, see you, dude, I'm going to hook up with this bicarbonate ion. The chloride says, fine, I'm going into the cell. Call me when you're ready. So it's transported back as bicarbonate. This is called the chloride shift, or yes, the hamburger phenomenon. You thought I was kidding. There is such a thing. Bicarb and chloride just basically exchange between the plasma and the erythrocytes, intracellular fluid. Carissa, you got a question? I don't even know what to ask. Okay. Carried three ways, 3 in the plasma, 3, let me rephrase that. CO2 is carried 6 ways, 3 in the plasma, 3 in the erythrocyte. Within the erythrocyte, because there's that enzyme carbonic anhydrase, CO2 is converted into bicarbonate and hydrogen ions. Hydrogen ions are buffered by the hemoglobin. That bicarbonate ion diffuses out of the erythrocyte into the plasma, and chloride goes in the opposite direction, so I have electrical neutrality. Now, it is very key that the relationship between how much bicarbonate and how much carbonic acid is present. Remember a few minutes ago I said that this is in direct relationship to this? As the amount of PaCO2 goes up, the amount of carbonic acid that's created goes up also. This is the ratio that I'm talking about. The amount of bicarbonate to amount of carbonic acid. Said another way, got more room here. I can express this as PCO2 times 0.03. So that denominator can be expressed in that fashion. This relationship is normally 20 to 1. In fact, we'll find that the measurement of this is looking at that relationship. The relationship of how much bicarbonate is present to how much PCO2 is present.
What's next to PCO2
times 0.03.
Oh.
Remember, we wanted to convert it so that they're both in milliequivalents per liter?
You said that's 20 to 1.
That relationship is 20 to 1. Okay. What's normal bicarbonate level? 22 to 26. What's the midpoint? 24. Agreed? Normal PCO2? 35 to 45, midpoint of 40. 40 times 0.03, 1.2. 24 divided by 1.2, 20. It's a 20 to 1 ratio. At a normalized pH within the range of 7.35 to 7.45, there's a 20 to 1 ratio between those two.
For the PCO3,
Yes.
you got that value by doing PaCO2 times 0.3.
Head of the class. You rock. Okay. Notice, first of all, that the range of pH within the body is an extremely small range. In fact, the range for the range that is compatible with life is roughly, I don't know, I'm guesstimating here, probably 6.8 to 8. Very small, narrow range that we function within. In our normal conditions, it's extremely small. Whenever that ratio becomes greater than 20 to 1, I'm going to say that the blood or the condition is alkaline. Whenever that ratio is less than 20 to 1, I'm going to say it's acidic. So technically, if we're talking about measuring blood, I could say that a situation where that ratio is greater than 20 to 1 would be an alkalemia. Where it's less than 20 to 1, it would be an acidemia. Or sometimes people will say it's an alkalosis and an acidosis condition rather than the measurement of the blood. Okay. Good so far?
I have a question.
What? You're interrupting my lecture.
Okay, for the H2CO3,
Yeah.
the reason why you're putting the PaCO2 times 0.03 is because as one
They're surrogates of each other, yes.
Okay.
We don't really measure H2CO3. We measure PaCO2. In fact, as Ashley will tell us, there's the three primary measurements we make in the blood gas lab are these three. We then calculate from that this value. So looking at this one, in order to create an alkalosis, what has to happen? In order to make that ratio greater than 20:1, there's two ways to accomplish that. I can increase the numerator or decrease the denominator. In either case, the ratio of the two of them will become 20:1. Greater than 20:1, excuse me. This is the crux right here of blood gas interpretation or classification. Is that relationship between bicarbonate and CO2. If, for whatever reason, the amount of bicarbonate ions in the bloodstream goes up, I create an alkalosis. If, for whatever reason, my PCO2 goes down, I create an alkalosis. By the way, is there a relationship between these two? Absolutely. What happens when I increase alveolar ventilation? What happens to PCO2? It goes down. They're inversely related. If you're hyperventilating, what kind of an acid-base status are you creating? An alkalosis. In fact, we're going to call that a respiratory alkalosis. Why respiratory? Because it's a respiratory problem. If the bicarbonate ion goes up, we're going to call that a non-respiratory, or more specifically, a metabolic alkalosis. We'll go over this again and again and again and again. The body's retaining bicarbonate ions for some reason. Yeah. There's some, without going too much in depth, there's some issues related to renal function that can cause that bicarbonate ion to increase. Can I make the assumption that if I said that this was the lung, you'd be okay with that? And we're going to find the bicarbonate ions are controlled by the kidney. They're regulated by the kidney. Kidney does all kind of, besides, making us pee, creating urine, regulating fluid balance, the kidney also maintains electrolyte balance, sodium, chloride, potassium, bicarbonate. And it also excretes waste products. That's a third function. Urea, creatinine, those kind of things. You guys have heard of urea, right? Okay. Wow. So I can create an alkalemia. I can create an alkalosis by either having an elevation in the bicarbonate level above 26. Let me say that again. Above 26 bicarbonate. If that's the cause, then I have an alkalemia, specifically a metabolic alkalemia. A reduction in PCO2 below the normal level of 35 as the primary mechanism. I have a respiratory alkalosis.
If your kidneys aren't working correctly, you would have a high PCO3 or?
Maybe.
Both ways.
It goes both ways. Right? Make a guess on how those can occur. Why would that ratio be lower than 20 to 1? The opposite. I lose bicarbonate ions, or I increase the amount of carbon dioxide in the bloodstream, which implies that alveolar ventilation has gone down. How are we doing? Two different ways that you can create an acid-base disturbance. Either something's happening metabolically or something's happening respiratory-wise. It's one way or the other. Should be. Yeah, Panopto records whatever is on my laptop. So, you think this is important? Mm-hmm. Yeah, huge, huge. Wow.
I know, I'm serious.
I'm serious too.
I saw like a little thing on it, so I knew it was coming.
Yep. All right. Before we go any further, let me just talk about what happens at the lung end. At the lung, you have a reversal of everything that happened at the tissue. So now I have CO2, which is attached to the hemoglobin. They part ways because the O2 has got to get onto the hemoglobin. So CO2 is released. Any CO2 that's attached to the plasma proteins, they're released. Bicarbonate that's within the plasma goes in the opposite direction. Picks up a hydrogen ion, forms carbonic acid, dissociates into CO2 and water. CO2 is eliminated. Bicarb is also moved back through the chloride shift, exchanged with chloride, back into the erythrocyte, where rapidly it's reconverted back into CO2 and water. So everything that happened at the tissue now is reversed. The 6 ways that they are carried, each of them are gone in the opposite direction. With, of course, the biggest one being the conversion of bicarbonate back into carbonic acid because of the presence of carbonic anhydrase, creating CO2 and water. Within the cell, CO2 diffuses back out into the plasma, into the alveolus. She came, she went. Now, there is a relationship between CO2 and between the dissolved component and the total amount of CO2 which is carried. Good news, it's linear, pretty much. Good news, it doesn't wiggle. It's just there. The effect of oxygen on CO2 carrying capacity is called the Haldane effect. Remember what we talked about when CO2 levels rise, O2 levels fall, the hemoglobin's affinity for oxygen goes down? It's a rightward shift with elevation in CO2. That's called the Bohr effect. Reverse that. What is O2 doing to CO2? As O2 levels rise, CO2 levels fall. Well, that's what you want at the lungs. You want them to swap spots on the hemoglobin. We're going to call this the Haldane effect. Bohr effect is CO2's effect on oxyhemoglobin. Haldane is oxygen's effect on the CO2 carrying capacity. And like I said, it's pretty linear. Thank God. That's all I got to say about that. Jenny. As the level of PO2 goes up, the amount of CO2 which is carried goes down. Okay, I can buy that. It's an inverse relationship. And I think we'll stop there.